Today, we're diving deep into the science of survival. We're going to explore the raw, incredible power of an explosion and the brilliant engineering that allows these massive structures to somehow stand up to it. It's that classic question, right? But for structural engineers, this isn't some thought experiment. It's a real fundamental challenge. The answer lies in this journey that happens literally faster than you can blink. And we're going to follow that journey step by step.
Okay, first things first, we have to understand the force we're actually up against. What even is a blast? It's not just a big push. No, it's a very specific, incredibly violent event that unfolds in just a fraction of a second.
So this is the core idea right here. Blast loading, it's all about two things: speed and intensity. It's this unbelievably powerful pressure wave that just slams into a structure and then vanishes in milliseconds. It's that sudden, massive spike of force that makes it so uniquely destructive. And this is a really crucial point, the difference between a static force and a dynamic one. Think about it like this. A static force is you leaning on a wall. It's slow, it's constant, and the wall has time to kind of spread that load out. But a dynamic force, like a blast, that's like punching the wall. Bam! The force is applied instantly, giving the material zero time to react in its normal way. So that dynamic punch has just landed. What happens next? Well, in those first few milliseconds, the structure begins this frantic, high-speed battle for its own survival. To really understand this high-speed fight, engineers track these 5 key responses. They're basically asking, how far did the thing move? How fast did it get there? How much did the material itself stretch and distort on the inside? And this one's huge. How did that initial shockwave literally race through the steel and the concrete? This data, this is what tells the story of those first critical milliseconds.
And this isn't just about skyscrapers. The research shows engineers studying everything, from massive steel box girder bridges and underground tunnels to large diameter pipes and even the structural frames of unmanned aerial vehicles, UAVs. Basically, any structure that's critical could be a target.
Of course, sometimes the force is just too much. And when a structure gets pushed past its breaking point, the results are, well, they're catastrophic. But from a purely scientific point of view, they're also absolutely fascinating. You might think that breaking is just breaking, but it is so much more complex than that. The way a material fails tells us everything we need to know about its properties and its hidden weaknesses. Now, this is what I find so interesting, the variety here. This is like a catalog of failure. Take steel beams. They're ductile, so they don't just snap. They absorb energy by bending and crumpling in on themselves. That's called local buckling. Reinforced concrete, though, it's brittle. It can be just sliced apart by the force in what's called shear failure. Seriously, think of a karate chop through a stack of boards. For masonry walls, the bricks are strong, but the mortar is the weak link, so the joints just give way and the bricks slide. And then you get something like a pipe, and you see this incredible adiabatic shearing, which is basically a rapid tearing where the force is so fast, the metal fails before it even has time to heat up. Wild, right? And this chart just lays it out so clearly. Researchers tested these masonry walls against more and more TNT. With 40 grams, you get some initial cracks. Okay, up it to 150 grams, and you see that damage spreading. But at 290 grams, it's total collapse. It's a perfect visual of that journey from just being stressed to catastrophic failure. But this story, it isn't just about destruction. It's really about ingenuity. See, for every one of those failure mechanisms, engineers are developing these incredibly clever solutions, smart materials, and brilliant designs that can absorb, deflect, and ultimately survive that initial punch. So let's look at a simple but really powerful example from the research. Just a basic steel plate. How does it hold up on its own? And how can we make it better? Yeah, no surprises here. You hit a standard steel plate with a blast, and it bends and deforms. A lot. It absorbs the energy by changing its shape, but it's left permanently and critically damaged. So that's our baseline. This is where the innovation really kicks in. The researchers didn't change the steel itself, they just added a protective layer, this specialized polymer coating. And the difference is just astounding. That coating helps absorb and distribute the blast energy, and it protects the steel underneath. We're talking about a dramatic reduction in damage. This one finding just shows you the power of using advanced materials to fight back.
And that coated plate, that's just one tool in a whole toolkit for defense. Engineers can reinforce materials from the inside, like mixing steel fibers into concrete to help it absorb more energy. They can isolate an entire building on what are called base isolators. They're like a giant suspension system for the whole structure. They can add stiffening rings to things like tanks to stop them from buckling, or they can retrofit older structures with steel jackets or a layer of something called UHPC. That's ultra high performance concrete, which is just ridiculously dense and strong.
So, at the end of the day, why does all this matter? Because this science isn't just theoretical. It's being used every single day to design safer embassies, stronger bridges, and more resilient public buildings. It's about protecting our critical infrastructure and ultimately protecting lives by engineering for stability in a world that can be dangerously unpredictable.
And that really brings us to the final crucial question: the science of blast resistance. It's a constant race between the forces of destruction and the power of human innovation. The research is always continuing because the need for stronger, safer structures is never, ever going away. The challenge is making sure our ingenuity always stays one step ahead.